We're going to begin our review of Chapter 3 problems. You can find these in the e-text starting on page 78. All right, so let me read the first one. It says, a sound wave moving through the water has a frequency of 256 hertz, and a wavelength of 5.77 meters. All right, so let's go over this real quick. So velocity is wavelength. Remember, that's the symbol lambda, the lowercase Greek letter lambda, times the frequency. Which is also equal to, because frequency is 1 over the period. This is also equal to the velocity lambda over the period. All right, so they gave us the frequency, so we'll use that. Just as a reminder, when lambda has to be in meters, the frequency has to be in hertz, and when that's true, when lambda's in meters, the velocity will be and the frequency, of course, is in hertz. The velocity is in meters per second. All right. Sometimes the wavelength is given to you in kilometers. If that's the case, the velocity will be in kilometers per second. Okay. So in this particular instance, it's very, very simple. They gave us a wavelength, lambda, of 5.77 meters, and the frequency was 256 hertz. All right. And then remember, this is sound, right? So it's traveling much slower than the speed of light. So this one's traveling at 1,477.12 meters per second. Here's problem number 2. It says, what is the wavelength of a 100 megahertz radio signal? Okay, so that's the important thing about that. Not only the units, is that we're talking about mega. Okay, sorry, that they're saying that this is a radio signal. All right, so radio, because then we know how fast it's traveling, right? If it's a radio signal, we know that it's traveling at the speed of light. All right, let me. I'm going to go over this in just a second. Let me just finish this for just a second. I didn't quite have room on my screen. So nano. So this is nano. I'll talk about these in just a second. Nano is times 10 to the minus 9th. And then the final one is pico. Well, I don't know that you need pico, but I'll put it in here. Just for completeness, is times 10 to the minus 12th. All right. And that's, I forgot to write pico, but anyhow. All right, so let's go back to the beginning of this. All right, and so we'll look at our problem. Notice it's 100 megahertz. By the way, that's in the FM range. They tell us that in the problem. So I want to talk quickly about what are called the metric prefixes. These are letters that are commonly used in science and engineering that represent some times 10 to the some power. All right. So the first one I want to talk about is tera. So it's always capital T, that stands for tera. So if you see some number, if it was 15 terahertz, you could replace the T with times 10 to the 12th. Similarly, if it had a capital G, that means giga. Okay, and so the G could be replaced with times 10 to the 9th. Mega, as we have in this case, could be replaced by times 10 to the 6th, which is exactly what we're going to do. And then kilo, of course, is times 10 to the 3rd. So like, for example, if you see a kilometer and you want to change it to meters, so if you want to change it to meters, you just replace the K by times 10 to the 3rd. Centi means times 10 to the, lowercase c means times 10 to the minus 2. Milli, which means times, lowercase m means times 10 to the minus 3rd. Micro, this is the Greek letter mu. Micro means times 10 to the minus 6th. Nano means times 10 to the minus 9th. You probably won't ever see pico in this class, but just for completeness, because we went from times 10 to the 12th, might as well go to times 10 to the minus 12th. And by the way, there are other metric prefixes. Anyhow, pico stands for times 10 to the minus 12th. All right, so I've written this. They give us that the frequency of this FM station was 100 megahertz. I just wanted to use the metric prefix, and you have to enter this in your calculator, right? So it's going to be 100 times 10 to the 6th. And like I've mentioned in lab, when we're doing this kind of thing, putting this in scientific notation, and you need to know how to do this with your own calculator. You never hit times, you never hit 10. You always have to use like the EE button or the EXP button. So you're never hitting times, you're never hitting 10. On the Casio, it's the EXP button. On a Texas Instrument, it's the EE button. All right, so you got to know your calculator, how to enter it in your calculator. Anyhow, so let's change 100 just for the heck of it. We don't have to do this. 100 times 10 to the 6th. We're going to convert that to scientific notation, right? So that means we have the 1. You put a decimal, and then since you have to move the decimal back to if I rewrote this as 1.00, you have to take those 2 spaces into account. So you have to add 2 to the 6 here, and that's how it's 1.00 times 10 to the 8th. I know a lot of people already know that. I just wanted to point that out. All right, and so in this particular case, they told us it was radio, and only all forms of electromagnetic radiation, all forms, travel at 3 times 10 to the 5th kilometers per second, or 3 times 10 to the 8th meters per second. All right, so we can solve this because we know this equation is true. Here, let me write it over here. So the speed of light is equal to the wavelength, lambda, times the frequency. All right, so remember, if we write the speed of light in kilometers per second, then the wavelength will be in kilometers. If we write it in meters per second, it'll be in meters. All right, so that's the way that works. Of course, frequency is in hertz, but hertz just means 1 over seconds. All right, so we rearrange this equation, and we're going to solve because it says what's the wavelength. So taking this equation, so this is basic algebra, really algebra 1. So if you how do you get the lambda by itself? You just divide both sides by frequency, right? Just divide both sides by the frequency. All right, and the frequency, of course, cancels on this side, and then it looks like this. Lambda, which is what we're looking for, is equal to the speed of light divided by the frequency. All right, and so this, now you'll see why we had to change it from mega, not change it, but put it in its numerical form, right? Otherwise, we wouldn't be able to enter that into our calculator. So this would be 3 times 10 to the 5th, and of course this is in kilometers per second. That's a K per second, and that's divided by 1.00. That's just showing the significant digits, times 10 to the 8th hertz, to the 8th hertz. All right, and so get your calculator out. Again, you want to make sure that you use the EE button. So here's what I'm pressing on mine. I know it's not appearing on the screen, but 3, and then I have a Texas Instrument, so I hit Shift EE to the 5th divided by 1 Shift EE to the 8th. All right, and so I hit enter, and I get an answer of 0.003 kilometers. All right, so that's the size of this wavelength. And just to remind ourselves, remember, kilo means times 10 to the third. So look, I could actually change this, right? If I rewrote this, this would be, 0.003 times 10 to the third, all right? And so times 10 to the third just means move the decimal place 1, 2, 3. So what does that mean? That, instead of kilometers, right, this would be, this would now be in meters, so it's 3 meters. It's a long way to say that radio wave would be 3 meters in its wavelength. Of course, its frequency is 100 megahertz. All right, let's move on to the next problem. For number 3, they say the normal human body temperature is about 37 Kelvin. 37 Celsius. What is this temperature in Kelvin? All right, so I've given you the conversion. It's the temperature in Kelvin is always 273 plus the temperature in Celsius. All right, so that's to answer the first part. What is the peak wavelength emitted by a person with this temperature? In what part of the spectrum is it? Okay, so we're going to answer all of those questions. Well, first of all, to calculate the peak wavelength, or what's sometimes called lambda max, and this peak wavelength happens for anything that's that is basically emitting radiation and it's hot. It's for thermal radiation. Okay, and so this peak wavelength is given. So you have the intensity on the vertical axis, and you find some peak. So this is something you can detect in your telescopes. And so the equation looks like this. This one here down below that I'm pointing out. This is actually really how it's used more often in astronomy. We measure the maximum wavelength and we calculate the temperature. Like, for example, if you want to know the surface temperature of a particular star, like the sun is roughly 5,800 Kelvin. All right, so in this particular problem, they want us to find the maximum wavelength. All right, so what is this value? They give us the temperature, or well, they don't give us the temperature, but you can calculate it. So you just take the temperature of the human body, which is 37 degrees, Celsius. Add that to 273, so that's 310 Kelvin. So that's the temperature of a human being. So then you put that 310 Kelvin in this calculation, and you will get what the peak wavelength that is emitted by a human being. And then we have to figure out what part of the spectrum that is in. All right. To finish this problem, we're of course using Wien's law. Okay. So as I said, it's usually rearranged the other way, where you're usually solving for the temperature, but in this case they're given the temperature of the human body. It has a temperature of 310 Kelvin, that is on the absolute scale, and so you take this constant, so it's 2.9 millimeters divided by that, and that gives us the answer. So the answer is 0.00935 millimeters. All right, so here's the thing. Millimeters, we're going to remember milli, the metric prefix milli means times 10 to the third, 10 to the minus third, right? So we're going to rewrite this. Okay, so this is going to be 0.00935 times 10 to the minus third meters. Now, the reason that we did it in meters, if you look in the textbook, this is convert. You can look at a table. All right. And actually, if you look at Figure 3-8, which is on page 66 of our e-text. The reason for that, the reason for looking at that figure is when we calculate this in meters, and of course I'm going to move the decimal place to put it in scientific notation, this is, you get this number, which is in the infrared.